So as you can see, our talk here is called Exceptions Considered Harmful. We'll get into exactly why that is. I think ultimately we'll end up more focusing on kind of alternatives to exceptions and the different strategies you can use to avoid just crashing your application and things like that. But just to introduce myself, I work at Lucid Software. We're a software development company in South Jordan. We produce the Lucid Chart and Lucid Press products, charting and kind of layout applications. I graduated from UVU, bachelor's in computer science, and generally I just really like programming languages, particularly with emphasis on functional programming, and a lot of that you'll kind of see later on in some of our code examples.
I'm Casey Allred, as it says. I actually used to work at Lucid as well, and then unfortunately, or fortunately, depending on how you look at it, switched to working with a company called Fans. You might have seen them in the malls and stuff. They have a brick and mortar store, lots of stuff like that. I'm helping them with their website right now. I went to school with Gregg. Have a lot of respect for him. He's a very smart kid. And relatively recently, finally finished my degree. And as it says there, I was asked to come help teach the lower level classes. So I've actually taught here at UVU as well, which was an interesting experience. You don't really know something until you actually attempt to teach it to someone. Just real quick question. How many of you here are like, you're here with your pitchforks, going to defend exceptions? How dare you take them away from us? And just curious, show of hands.
Nobody.
Okay.
Okay.
Good. How many here are just like, I hate exceptions, but I can't get away from them? Like, what do I do? Anyone there?
A couple.
Awesome. Okay, that's where I was. I was just curious.
So the rest of you are maybe like, they're what we
Or
use.
it's like, yeah, we're bored. We'll come to this one.
We'll see what else there is.
Better than the other talk.
Yeah.
Well, good. We're glad you came to at least see us.
So I think in general we want to keep this kind of casual. So if anyone has any questions, feel free to raise your hand, and we can kind of keep it an open discussion, especially as we get into the code, because we're actually using a couple programming languages that aren't super popular. So that'll be fun. Actually, just as another quick poll, how many people here are familiar with Scala? Cool. So we've got a few. That's actually more than I expected. Awesome.
What about Rust? Yeah.
It was like the same people though.
That's awesome.
How about Go? Anyone know Go?
Wow.
Do that. All right. So those are the three main examples that we'll have. So that's actually about half the room knows at least some of those. All right. So on to exceptions. Everyone's familiar with the idea of a go-to, right? You say go-to and you just jump to some arbitrary point in code. It turns out that's basically what an exception is. You say throw this and somewhere else in the code. We don't know where, but somewhere else in the code we're going to deal with that. People like it because you get to kind of punt the responsibility for dealing with errors. You get to say, I don't want to touch this right now. I think that's a bad thing because you get this potential for spaghetti code. You have these, so I did some Android development just a little bit kind of on my own with Java. And you end up with these kind of nested try-catch things, or like these series of try-catch blocks to try to catch all the possible errors. And like one function throws like 13 different possible exceptions. And you have to catch them all, because if you don't, something's just going to crash. Or you just ignore all of them and catch exception and move on, right? So it kind of defeats the purpose of error handling to begin with. And interestingly, this point here about the modern go-to, I believe C#, Go, and I can't remember the other language. I think even C actually requires that the go-to stays within the current scope. You can't actually escape your scope. Whereas with exceptions, you can just jump out and run away, and who knows where you end up.
And I think the biggest, I guess, problem that you experience with like with the go-to and with exceptions is that you could leave your system in an inconsistent state unless you like took all these precautions and did things in the right order and stuff like that. And you don't necessarily have a compiler, like the compiler doesn't necessarily able to tell you that you did it wrong all the time, right? Like there are, some catchable exceptions or whatever, or checked exceptions. Sorry, that it can kind of help you with, but otherwise you're kind of on your own. And as someone who has programmed in PHP most of his professional career, that's not very fun. You're left to fend for yourself via some sort of like unit tests or just walking the code as much as possible. So,
how many people here like checked exceptions in Java? I mean, I don't know if you've experienced those or used those, but I think the general consensus is that they're kind of a headache, and they like make you either say throws or catch all of these weird error cases, or just catch exception and ignore them. And I think that's not the approach that we should be trying to take to make reliable software. Yeah.
Oh, whoops.
That shouldn't happen. Yeah, so general pitfalls is that we end up with this overuse of exceptions. Everything that throws an exception. Like if you have a string and you call toInteger on it, if that string is not the right format, exception, program crashes, right? And then you get into this case where, in that case, you get something like a number format exception. And we have all these like kind of an exponential growth of the different types of exceptions that could be caught. And if you're in an environment where you don't have checked exceptions, you basically have to know about all of those beforehand, or your program will crash, or you ignore all of the errors. And there are exceptions to these rules, right? They're still probably okay for certain exceptional circumstances. The one that sticks in my mind the most about when you probably can't do anything else but throw an exception is when you run out of memory. I think that, what do you do, right? You're in a really bad state at that point. So I'm trying to avoid inflammatory statements toward exceptions, but we do have this one quote here. It says, exceptions are the primary error handling mechanism employed by many widely used languages. They are also a side effect that makes a liar of the type system and makes local reasoning about code far more difficult. They represent an undeclared method result smuggled through a back channel separate from its declared return type. Furthermore, they transitively become an undeclared result of anything that calls that method, and anything that calls that, and so on. Trying to reason about the correct behavior of code becomes very difficult since the return type can no longer give you enough information. Exceptions kill modularity and inhibit composition. So I don't actually really know much about who Ken Scambler is, but this blog post, Abject Failure of Weak Typing, had this quote, and there's a link there if you want to grab that down. The rest of the post is actually really interesting as well. But I think this quote kind of summarized my feelings about exceptions more effectively than anything else I've read. Basically, when you call a function and it can throw exceptions, the return type says integer, but all of a sudden it also kind of returns number format exceptions, or I don't know, some sort of IO error or things like this. It could be any number of things that it also kind of returns. And there's no way to really know beforehand unless you read the code or already know, right? Like it's just a matter of having that prior knowledge.
And one thing I personally really like about this code is it's talking about the type system, right? And one of the problems is that the exceptions are not encoded in the type system, and so you don't have any assistance from the compiler to help you manage them properly, right? Again, except for the checked exceptions, but even then it becomes quite difficult. And so I also like functional programming and getting more and more into it. I've come from a procedural and object-oriented background, but so if you think about, I'm trying to get partial functions out here. You have like a function like a division function, right? That's kind of the quintessential example. And you'll take the numerator and the denominator, and then if the denominator is 0, like, oh no, we can't divide, right? That's mathematically incorrect, right? And so oftentimes that's when, throw an exception or something, right? I don't know. And it's much better to take that, instead of having it being a partial function where there isn't just a one-to-one mapping between the input and the output, or excuse me, you turn it into a real function where there is a one-to-one mapping, and you encode that possibility of failure into the type itself. And that's kind of where we're going to with, or at least, maybe not even the type, but just at least the return type itself, I guess I should say.
Yeah, so exceptions are bad, but there are alternatives. We're not just left trying to not have errors, right? Because that's not reasonable. These are the main 4 alternatives that we're going to talk about. There are probably lots of others. If anyone has any, feel free to shout them out. But these are the ones that we I think are the most common anyway. We have multiple returns. Go employs that a lot. Same idea as return tuples. The option or maybe type, Haskell and Scala use that. I think Rust does as well. I think we have an example of that.
Yeah.
Then, yeah, we'll talk about what each of these are in turn.
I guess one thing that we didn't put on there, and mostly because I don't really like it, is that you have some sort of like part of your possible return values that you return as the error code, so to speak, which is often like C is what you end up doing, right? So, and that can get a little messy because you're intermixing your error values with your real values, and these options that we provided here still allow us to segregate that, to have your actual values with your error values separate, but still encoded in the same return type. So.
Yeah. The focus on these is to, like Casey was saying, to make sure that we have total functions instead of partial functions, right? So if you have a function where you pass in an integer, and that integer can be any integer, right? But if it's 0, you're going to get a divide by 0 error. That's not a total function. That's a partial function. It doesn't have an output for 0. Whereas using these methods, we can get a total function where you actually do get an output. It's maybe not an integer, but it is something that you can do something with. Yeah. So. Okay. So we're going to cover some examples. Any questions starting off here about kind of any of these ideas? I think it's pretty straightforward so far. All right, so we're going to have kind of a bunch of examples now. We're going to start with this Go one.
Is that readable? Is it big enough?
That's probably all right. Anyway, you can talk about this one.
Yeah, okay. So I'll be honest, it's been a little while since I've programmed in Go, but I actually wrote... Oh.
The red button.
Wow. Okay. So it's been a while since I programmed to Go. As part of UVU's Capstone class, we actually have to write a compiler and a virtual machine, and I did mine in Go. So it was actually, I found it a joy of a language to use, but I haven't done anything since then. I've been mostly using other languages. But what you end up doing, like, so this is the type signature for opening a file, right? And instead of just like returning nil, if there is if it's a file, like instead of this file pointer being nil, if there's an error or whatnot, the proper way is to actually return this error type. And that error type, if it's set, if this is not nil, that means something went wrong, and it provides a little bit more information alongside with it. So some people complain that it adds extra, like, you have to always check right after. But I found that as I was using it, even on that, let's see how many lines, it was about 8,000 lines or so, so not extremely large, but definitely it's not a small program that I wrote with it. It actually wasn't that bad, and it was great to see the explicit handling of errors. As I was going through and reading the code, because the virtual machine you programmed in the one semester, and then the compiler in the next, right? And then the compiler had to create a program that runs on the virtual machine. So I'd have to go back and look at my code that I wrote, 6 months ago, and actually understand it, right? And because of this kind of pattern, it was really simple to just read and understood it right again. Like, it wasn't. I'm assuming we've all experienced that, where you write something and then 6 months later you look back and you're like, what? Like, where's this error going, or how's this doing? And because of the simplicity that's provided, it makes it really nice. Like, you just read it through, and the flow, you can see exactly what's going to happen, when, where, and how. So I actually see that as a benefit. But yeah, like I said, it's the multiple returns. So this right here is how you accept multiple values in Go, as I'm sure most of you know. and then you just check it right after, and do whatever is necessary. Fairly simple, right?
Yeah, I think this is a good simple approach. It's super readable. Basically, everyone can glance at that code and more or less understand exactly what's going on. That we have an error, and we have an error value, and if that value is not nil, we handle it, right? We deal with it. I think that this definitely has some weaknesses. It can get a little bit verbose, and it's kind of a Anyway, it's a neat approach.
Okay, so I wrote this. Actually, you can compile it and it'll work, and you can see the output right here. Oh, whoops. What this option is in Rust is they call it an enum, and basically the value of an option can either be sum with something embedded in it, or none, and that's it. So like you could have a sum with an integer in it, as this points out, right? The option I32. So we pack that integer in the sum, and that means it worked. We're good. We can also have the same type here with an option that's integer, but just return none, which means something went wrong. And the way that's really nice is, or the thing that's really nice about this is because they're encompassed in this parent type, so to speak, we can compose them all together and use them together in a chain of commands. And so the and then function here is it execute this if it's still a sum. And the or else function says execute this is a lambda in Rust, in case those don't know. It says execute this function if we're a none, right? So it's a way that you can chain them together, and then if there is an error, you can do something else to kind of recover from that. All staying within this parent option type, right? Which is really nice. And you see as we print out, this means to print out like it's debug in representation. So we see this sum 42 is what comes out because we called this does not work, which turns it into a none. And then since it's a none, it will execute this, and so it returns this sum 42. And then if we want to get it out, right? So eventually we're going to have to display this to a user or return it from our web request or whatever, right? And we're not going to send back a sum over the wire, what per se. We can unwrap it to get that value out. And the preferred way to do that is to unwrap it and then give it some type of default value. I just arbitrarily chose 10 here. So that if it is indeed a none, instead of panicking and crashing the program, we just swap in that default value and continue on with the execution. So, any questions about how that works together? I know you guys said you're fairly familiar with Scala and Rust. So.
Yeah, I think this option type is kind of important to understand because it's kind of the basis for the rest of the examples. Basically, you have sum and none, right? Sum has a value, and none just means it didn't work or there's nothing there. And it's kind of a neat tool that's come popular. This is actually the exact same example, but it's using Scala because I like Scala better than Rust. But it's effectively exactly the same. Grammar's a little bit different. We use flat map instead of and then from the Rust example, and get or else, or else. I think that was actually the same. And then get or else there on the second print line. But I don't think there's anything remarkably different between those two. They're roughly the same code, and they behave identically.
Okay, so the next type is, what if we want to have something a little bit more than just none, right? We want to, so options work great if there's only one way to fail. So in our dividing example, dividing by 0, that's basically the only way that you can fail in that division. We'll pretend. Okay, so that's perfect for that. But what if there's 15 different ways to fail, or we want to provide a specific, message when it fails, etc. We use what's called a result type in Rust here. And what we do is we have to tell it what the success type is going to be and then what the failure type is going to be. And everything else is essentially the same as our option example, except for instead of wrapping it in a sum, we wrap it in an OK. And if it fails, we wrap it in an error. And as you can see, the output here is just OK 42 because we end up falling into this or else and returning the 42. And then when we unwrap it, we actually get our value.
And again, Scala example, very similar. There's a little bit of difference. Scala has a type called either. It's a little different than result. Either is not biased to one of the string or the integer, right? Where's that laser pointer? It's right there. So either says our left side is a string and our right side is an integer. So basically it contains one of those two values, either a left of a string or a right of an integer. And so we call this function does work and say we want to bias ourselves to the right side. And that basically just means that the integer value is our success value now. And then we call flat map on it, which just lets us apply a function to it. And again, we bias the result of this does not work to the right side. And to kind of just because the same thing, we want right to be the success. We want integers back from this. And then this fold function on either takes two lambdas. The first one is our right. So if the result of this flat map is a right, we'll run this function here, right? And if it's a left, we'll run this function. Ultimately, we want to get out a right of an integer. So what we do on the success value, we just pack it back up in a right and return that, right? Because we got what we wanted. On the error value, we pack up some other value, some default sentinel value, whatever it is. We get 42 in that case. But then otherwise, it's basically the same. We output right a 42 or 42 in these two lines here. Yeah, so you can see that this basically is the kind of OK from the Rust example. Yeah, so that's a pretty cool type. I think that's really useful. And yeah, so then there's this thing called validation, which who here has had to do like form validation on an HTML web page, right? I mean, probably most everyone has done something like that, where you have to go through all the fields. You have to see, is this one right? Is this one right? Is this one right? Is this one right? And then you return an error. There's lots of websites out there that you'll like, I don't know, get the first field wrong, like it's not the right address format or something like that, and you'll fill out everything else, and then you submit the form, and then you get back, oh, your address is invalid, and so you get that error. So you fix your address, leave everything else the same, submit it again, and you're like, oh, this phone number format's invalid, right? It tells you things one at a time, and that's how a lot of error handling is, right? You check some condition, as soon as you hit an error, you stop and you jump out. And handle that error on the spot.
Which is how the option and the results and either work. So
yeah.
Forgot to mention that.
Yep. So you have basically one chance to catch the error, and deal with it in the spot, and report back on that one error that you caught. With this validation object, it actually comes from Scala Z, which is kind of a cool functional programming helper library from the Scala community. And it adds lots of really confusing things like this bar at bar operator and things like that. For better or worse, I don't know if I love that, but it does that. But anyway, the idea of this validation is that you test all of the conditions, and then you report back the failures that you got from that, or the successes, right? So we have these two functions right here. We'll look at fails. So this right here basically just says we did something and it was a success and it's an integer, right? And then you also have to put this string in here just to say that it's a validation of those two types, an int and a string. The string being the failure and the int being the success again. So we have a success and we get a 1, and then we have a string that's a failure, frowny face, and then we have another string that's a failure and a frowny face. And so what happens when we run that? We call that function. We get back this validation result. And then this thing right here is a little confusing, but basically what this says is take the first parameter, or the first validation, the second validation, and the third validation, and just add them together. So it takes the value of this, and this, and adds them, or concatenates them, because we're dealing with strings too. Since f ultimately returns a failure of a string, this guy gets set to basically an empty string, the default string value. So we end up with an empty string plus sad face right there. When we print it out, we get two sad faces, right? So we went through all of the steps in the process and not just the first failure, right? We didn't just get one sad face, but we got all of the sad faces. So that way we can just have more robust reporting on the condition of an operation. And then for the success case, we got all successes along these, right? We have 1, 2, 3. But we do the exact same thing. We add them together again in the success case. And in that one, we end up printing out success 6, right? So we get kind of a cool thing where these same 2 lines of code, whether it's a success or failure, ends up working correctly. Now, of course, the function that you give it right here, whatever operation you give in here, has to work on both types. Otherwise, it's not going to work. But like if, yeah, I don't know, if since strings support the plus operator, this works, and since integers support the plus operator, it works, right? Because they need to be consistent to be able to do that. But these functions here can be anything you want. Those could be multiplies. You could take the integers, throw away 2 of them, and just triple 1, right? You can do whatever. These are just functions that you're passing. This is just kind of Scala's syntactic sugar for that. And yeah, so it's a function that takes 3 parameters and adds those 3 parameters together. So we get the 2 different result types there, which I think is a really cool thing. Now, this is kind of neat, and it's fun to see and play with it like this. But you can also do things. There's like an is failure and is success on this validation thing. So you can actually check to see if you succeeded or failed before you do other things. And that can actually inform your decision of which function you want to call on the result of that, especially if the things you want to do here are incompatible with the success or failure case. So you can do neat things like that. So.
Yeah, personally, I think that this concept is actually one of the most real-world type of things that you'll probably use. Well, I guess that's not fair. What I've done a lot of is the most real-world stuff because of like your form validation, like you mentioned before, or like running various tests. I used to do a lot of testing when I was at Lucid, and you would want to run all of the tests that aren't dependent on each other and get all of the results back so that you can fix the according one, not just the first one that fails per se, right? So this methodology is great for that kind of stuff.
Yeah, so validation. So one of the things that was mentioned in that quote earlier is that exceptions inhibit composability or composition. And so I want to actually kind of demonstrate some kind of live examples of that real quick. Not necessarily of inhibiting it, but showing how these types that we're talking about here actually really help with composition. So I've got this REPL here. That might be a little hard to read. Let me see if I can get something a little bit better. Let's bring this guy over here. So, yeah. Oh, bigger? Gotcha.
Is it 15 minutes?
Yep.
We said 15.
15 minutes. Gotcha. Okay, so this is just going to be in Scala. Can everyone read this? Does anyone want it bigger? Everyone good in the back? Okay, cool. So I don't know why I just did that. Yeah, so I'm going to import something real quick. Whoops. Right, so what we want to do is we want to look at how these things are composable. So we're going to get a couple functions. We'll do a returns option int equals sum1, def b option int equals sum2, def c option int equals none. Yeah, so we've got those three functions. They all return an option. And one of the really cool things about these, especially in Scala, I don't actually know if Rust has the same idea, but you can actually compose these using a for yield syntax. Anyone familiar with Haskell? 1, 2, yeah. So it's kind of like the do return in Haskell. Same kind of idea. But basically, you have this, and you say like x, and we want to get the option from a, right? So we're saying we're going to take a here. It returns an option, which is a sum of 1 in this case. We're going to unpack it and put the 1 into x. That's basically all that says. And then we're going to do the same thing on the next line, where we're going to unpack the b now. And yeah, so exact same thing going on there, and then we're going to do the same thing with the z, or with c. And now this time it's a little different because c returns a none, right? So it doesn't have anything to unpack. So we'll execute it real quick and just yield x times y times z. So when we execute this, we'll do. I can't press Control B.
Control C, Control D.
Oh, wrong button.
Or you're an Emacs.
Control D is not working. Well, that's disappointing. All right. Is there maybe an external keyboard here or something? There's a lot of wires here. Well, I don't know how to get out of paste mode without Control D. That's really strange. So we'll just try this again. That's not what I wanted.
Is everyone familiar with close to familiar with Scala? Have you used the for yield syntax at all to compose things? Yeah.
All right, so we'll paste this in here. And that should execute, and we end up with none. Basically, what happens there is, let's just get rid of that guy. Yeah. So basically, what happens is we get a sum there, we get a sum here, but there's none here, so the whole thing is a none, right? We can't do this computation anymore because we don't have that third value. If we changed C to say option int equals sum 3. And then put that back in. This time we actually do the calculation. We get a sum of 6 because now we have 3 values. And then same idea if we changed b to be none. And then we run this. Now we get none again because now b is missing. What actually happens is that in this case, it hits B, and then it actually just jumps out right there. It doesn't even try to do C, which is kind of nice. So you don't do computations you don't need. But this lets you compose things that have a type of option together. You can kind of chain those things and say, if all of these things have a value, if all of these things are a sum, let's do this computation on it. Otherwise, we still have a none. We just stay there.
This for yield expression could be in another function somewhere else, and then composed with another one that has a for yield, so like you can nest them down in and compose those even more, right? Because they're all under the umbrella type of an option, right?
Yeah. Any questions, thoughts about that? Yeah.
I've noticed that all these examples you've given us they have inherent mechanisms, that give you these ways of doing things. Most of us are stuck in the world of Java.
Sure.
Exceptions are the norm.
Yes, that's very true, and that's actually a good point. So all of these things, like this is actually just syntactic sugar for something else. So if we did a dot flat map b dot flat, or I think we'll do dot what is it? Flat map c I think then you do. Is that right? I can't remember.
And then map X.
Oh no, but these need to be.
Yeah, they're nested a little bit.
Yeah.
It's the joy of. It's why there's a nice syntactic sugar for it.
Yeah. So these are all. So I guess let's just do 2 levels. Let's say we're just doing the X, right? So we're going to do B flat map. We'll just do 2 levels. So we'll call map on the inner one. Y, and then we do X times Y, and then we close those things off, right? So that's the same thing, right? So this right here is the same if we didn't have that third line, right? So it's just function calls. This is just syntactic sugar for this. So even if you're stuck in Java, especially with Java 8, now that you have lambdas, right, you can do things just like this, provided you create this flat map function, right? You'd have to, there needs to be some infrastructure, but all of that can be added through libraries. They're not necessarily required language
Java
features.
8 introduces an optional that has a flat map.
Yeah, so there you go. Java 8 introduces a lot of these types of things. Which
I was just going to say the flat map is just a map reduce, essentially, so you could mimic it. I couldn't remember if it had a flat map, so thank you.
Yep.
And there is map reduce in JDK.
Yeah. Okay.
Yep. So, So it's just yeah, and like you said, you brought up a good point that exceptions are kind of the norm in the Java world, right? Like if you use any third-party library that's a Java library, it's gonna throw exceptions. Do we not have that slide?
Oh, there it is. That's what
Oh yeah, okay. It's going to throw exceptions. There's not a whole lot you can do about it. But yeah, and like I said, out of memory and third-party libraries are kind of the exceptions to the exceptions rule that we're presenting here. Maybe there's others. Does anyone think of anything else where you think that maybe that definitely you should fail and throw an exception? I couldn't think of any others.
Or I just have a different idea, I guess, because I've been struggling with this idea of exceptions for a while. Isn't there like another option that we haven't explored, for example, like the divide by 0? We define that as a function that takes in like 2 numbers and divides them, so you can either get an answer or you can get an exception. But we're just not defining what division by 0 or division actually is. Because division is taking one number and then another number that isn't 0 and returning a result. And so it seems to me that isn't there a way that we can tell the compiler, hey, the second number is not 0 ever, so there is no chance that we can fail?
Isn't that the validation stuff?
It kind of, right? So the validation happens at runtime, right? That's just a tool to check your inputs and see if they match some rule that you have. I think what he's saying is that he wants a compiler to guarantee that this function can't be called with a 0 passed in as that second parameter. And that's a really cool idea. I don't know off the top of my head how you would do that for, what's that?
Dependent types.
Dependent types?
Yeah.
Explain what you mean.
Those are types that have logical constraints within the type system. So you can have a type that's greater than 0.
Yeah. Or a non-zero, like a non-zero integer type. Yeah, exactly. And that's exactly what I was thinking.
Like user input, right? I mean, at runtime it could.
Yeah, right. So when you're trying to
dependent types, it's at compile time when it's doing type check, it actually figures out if it's provably non-zero within the program.
Yeah, something that I've used a lot that is similar to that is the idea of a non-empty list. I've been using that at Lucid lately, and it basically says that we have this list of data and we can guarantee that it's not empty, right? So I can shove that list into an SQL in clause without causing that exception on the empty parens thing in there. And so it's a very good idea, yeah.
Another thing that some languages do is that you can use data new and just have it be limited to whatever set of data that you passed in. But that's kind of harder to do when you want all integers.
Right, yeah, right. You have like 2 to the 32 values. We have enumerated all of those, right? But that's a lot. But yeah, for more limited functions, that idea of a total function, you have this limited set of input. There's 10 new values. Those are the only things it could take. You have a guaranteed output for each of those. Same idea. Your dependent type, your non-zero integer, guarantee that you can always divide by that number. Kind of a neat idea. On the idea of the third-party libraries, we don't always we don't have control over third-party libraries, but Scala provides this cool try construct that's kind of fun. This guy right here. It's called try, but it's not a try-catch. It's a little different. It's a capital T try. Basically what it does, it says execute this. If there's an exception, let's pack that up into a value instead of just throwing it. And now we have a value, so we can work with values, and we have like constraints about these types of things. So then we can take a look at this. We can unpack it and compare it. We say, basically this just says, if this is a success, do this. If this is a failure, do this, right? So in the success case, we can carry on with our computation. In the failure, we provide a default value. And so this just simply throws an exception, right? It has the int return type, throws an exception. So you can see the output. We get a failure with the out-of-memory exception wrapped up in that. So you can still do all the nice things that you have with the exception. You got your stack traces and all the overhead that comes with throwing exceptions is still a part of this. But you can kind of abstract away the idea of trying to recover from all your exceptions immediately and recovering from every possible type of exception whenever you can. Of course, this isn't a whole lot different than try-catch, right? I'd say it would be more fun, better to just not use libraries to throw exceptions, but that's not practical at all. And so this just adds some neat library features around handling and dealing with exceptions. Yeah,
I actually used this quite a bit when I was creating a functional interface to interact with the Selenium WebDriver. And Selenium, the client in Java, I guess it is, loves to throw exceptions for all the things. And so I leaned on this heavily to provide that abstraction so that I could deal with Selenium in a more functional paradigm. So it works really well.
Yep, and I didn't show examples of it, but both the either and this try are composable in the same way that those options are. The either, you just say I want the right or the left to be the success, but then you can compose them with the flat map function and kind of chain them, and if you get a failure at any point, it jumps out. Same with this. It does basically the same thing. You could throw this into the for yield or use the flat map on it.
It's essentially an either that's certain association. But.
Yep. Yeah. So. Didn't mention it before, but basically all of these things are monads. If you know what those are, cool. If not, don't worry about it. It's kind of interesting though. Yeah, so that's it. Any questions, thoughts, comments?
Actually, dude, can we go back to like the first example that you showed, and it had the success function and the failure function?
Let's see, where is that?
Which one are you looking for? Like
like that, like right in here.
This one here?
So you have a function that does work and function does not work. And I'm assuming that you can have multiple reasons why something doesn't work.
Sure.
So are you going to have a bunch of statements in here that are trying to figure out what the reason is and return like
so you mean like in here?
Yeah.
Right here?
Yeah.
You might, right? So like this is the worst way to like represent an errors with a string, right?
Yeah.
But it's easy to look at.
No, but you might like want to throw individual codes based on like what the problem is.
Yeah,
So
correct.
can you talk about what the difference is between how you're presenting it, where it's a function where I'm going to have to do that work anyway, versus I'm just going to set up a specific catch block for each exception anyway?
Yeah, so it's not necessarily about doing more or less work, right? Because error handling is error handling. You're going to be doing the same amount of work no matter what. But the idea is isolating the work to one spot. This is where you handle errors. This function can fail, and so we need to take this result and handle the error on that, right? We need to make a decision right there. It's about dealing with values. Exceptions are kind of something else. They're kind of a value, but kind of not, because they kind of transcend the environment that you're running in, right? They just throw and explode, and if you don't catch it, everything's dead. Whereas if you don't deal with a particular error, maybe you'll have bugs in your program, which maybe is worse, but or you can just crash it manually, right? Like if you want to crash, by all means throw an exception. If you don't want to crash, deal with your errors as soon as you can.
Well, I think what we're getting at is most people throw exceptions so that the caller is responsible for handling it. Right? And is that not what's going to be happening?
Well, the caller of this is responsible for handling that error, correct?
Yeah.
And that's the idea, but it's encoded in the return type now instead of just being an exception that might get thrown. Now you have to deal with both cases of failure and success.
We're actually close out of time, and I know you guys want to get to lunch, but I was just going to mention one thing that's slightly different than the catch with the multiple catches is that in Rust, if you wanted to unpack the error per se, you would do a match on it. and the match statement knows, like, you'd probably use an enum instead of a string, right? So some sort of like type that indicates all the different types of errors, and it'll know whether or not you've actually handled all of those errors or not. And it can give you a compile time error if you're not actually handling those. So it can catch up if you forgot the, doesn't compute exception, error. It'll be like, hey, you didn't handle this. And you'll be like, oh, well, thank you. I will actually handle this now, right? So that is one benefit that you get as opposed to the try, catch.
Mm-hmm. Yep. This just puts more responsibility on the caller to deal with it because it's encoded in type. Exceptions are easy to ignore. Return types are less easy to ignore because you usually want the result. But yeah, I think that's probably about it as far as time goes. We'll stick around if anyone else has any questions.
Yeah.
So
thank you for your comments. We appreciate it.
Thanks, guys.